In the last class, we have derived a relation between the refractive indices on both sides of a spherical surface that separates two media like air and glass. So, today we will apply that theory to a thin lens. The thin lens has been shown in the figure. It has two surfaces, 1 and 2, having radius of curvature R1 and R2 respectively. So, for simplicity, we have taken a point object O that forms a point image I due to rays, one along the principal axis and the other along the direction shown in the figure. Let us say it is OL and this is a M. So, how to apply that theory, previous theory, to this case? Because it has two surfaces and the refractive indices are also like air, then this is glass, then again there is air. Let us say absolute refractive indices are N1, N1 and it is N2. The thickness is T. So, let us first apply the refraction at a spherical surface theory to the first surface. Refraction at a spherical surface be applied for the first surface of the thin lens. You see, actually the final image is I due to refractions at the two surfaces. But how to apply the previous theory for the first surface? For the first surface, object is O, not problem, but image is at I1 if there is no second surface. That means we have to think that the first surface separates air and glass altogether. So, the first image is at I1 which would have been formed had there been no second surface. So, therefore, what to write? You see, we can write N1 by U plus N2 by its distance from the first surface is V1 plus T is equal to N2 minus N1 by R1. So, this is first equation. Then what to do? For the second surface, refraction at the second surface, we know that the final image is at I, at a distance V from the pole P2, but the object is at I1 in glass. So, that thing has to be remembered, that for the second surface the object is at I1 in glass forming a real image in air. So, for refraction second surface comma object is I1 in glass forming a real image I in air. So then that theory, refraction at a spherical surface theory, when applied to this one, this is for the object distance and refractive index of that medium. So object is I1, so refractive index for that medium is glass. So N2 by V1, N2 by V1, then this V1 is now to be taken as negative, because the rays travel from I1 to second surface and you are measuring from pole P2 to I1. So the directions are opposite, one is from right to left, another is from left to right. So that is why a negative sign is associated with this one. Then for the object distance, this is for the object distance, and there is image distance. Image is measured from P2 to I, so that is positive. So that is N1 by V is equal to final refractive index is your first. So final is air, so it is N1 minus N2 by R2. So this is for the second one. Then you can write the negative sign is due to the sign convention. Sign convention gives you the negative sign. Then what to do? We will apply the thin lens. Thin lens means T tends to 0. So then we can write for a thin lens, this small t, that is your thickness, tends to 0, so that equation 1 becomes this one. Here object distance can be taken as negative. Same thing, you can take negative for this one. That is N1 by U, then this is the third equation. So now you can add. So adding equations 2 and 3. Adding equations 2 and 3, comma, we get, you see, N2 by V1 cancels. So you have N1 by U plus N1 by V is equal to, here it is N2 minus N1. N2 is greater than N1, so you can write here, you can introduce a minus sign here. So it will be N2 minus N1 by R1, then plus of minus N2 minus N1 by R2. Then what we do? We have to take N1 common. From this you can take N1 common. So N1 into 1 by U plus 1 by V is equal to N2 minus N1, then 1 by R1 minus 1 by R2. Then if you divide by N1 to both the sides, divide by N1 to both the sides, so what we get? We get 1 by u plus 1 by v is equal to n2 by n1 minus 1 into 1 by r1 minus 1 by r2. So, this is your final equation, which is called Lenz-Maker formula. Then actually two cases arise. Special cases. One is for the double convex or biconvex, you can say double convex lens. You see from this formula number 4, if R1 is equal to R2, then it will be 0. So, this side becomes 0 and u is usually negative because object is on the left of the pole. So, 1 by v minus 1 by u, that is your Lenz equation, and that is 1 by f. So, 1 by f is equal to 0 implies f is equal to infinity, which is not the case. In practice, a thin lens produces a focus a few centimeter away, that is experimentally found. So, naturally question arises about the correctness of equation 4, which is not incorrect, but how it will explain that f is infinity. So, that is why they have developed a sign convention, like the radius of curvature R1 and R2, they have to be measured from the curve towards the center. If a ray moves along that direction, so that R1 is positive. In this diagram, you see from 1 to C1, that is R1, so it is along the direction of the ray, so it is positive. And for R2, it is against the ray, so it is negative. So, that we will explain with the help of another simplified figure, same. So, this is 1, 2. This is say C1. So, this is your R1. So, R1 has to be measured like this. Then your ray direction is so ray is moving like this. This is object. So, R1 and R2 are to be measured, from the curve, towards the center, So, here R1 is having the same direction as the ray. So, R1 is positive and R2, which is measured like this, R2 is negative. So, in that case, what will happen? Equation 4 will be then equation 4 gives 1 by u plus 1 by v. Some people confuse that this is mirror equation. It is not mirror equation. U is negative, so it is 1 by v minus 1 by u. We have not written because u data is not given, so we have written like this. Where u is negative, it is understood. So, it is n2 by n1 minus 1 into 1 by r1 plus 1 by r2. This is 5. Then special case number 2. biconcave or double concave lens. So here the sign convention for the radius of curvature this is C1, this is C2, so this is R1 and this is R2. You can see that the ray is from left to right. So R2 is along that direction. So R2 is positive and R1 is negative. So R2 is positive, R1 is against the ray direction, so R1 is negative. So the equation becomes, so equation 4 becomes, this is say positive, so altogether you have a minus sign, and it is 6. So this also satisfies that f is negative. Due to this negative sign, f is negative, and here f is equal to positive. So the power of the lens, as you know, power of the concave lens, power of the lens is equal to 1 by f in meter is equal to negative for this one, and for this one P is equal to positive. For the convex lens power is positive, for the concave it is negative. Then to introduce that focal length in this formula, we can use 1 by v minus 1 by u is equal to 1 by f directly, or you can say if the object is at infinity, the image will be at the focus. So image distance is equal to focal length. U tends to infinity. So when u tends to infinity, comma v tends to f. So equation 5 and 6 become 1 by f is equal to n2 by n1 minus 1 into 1 by r1 plus 1 by r2. This is for the convex lens, say 7, and for the concave lens it is with a minus sign 1 by r1 plus 1 by r2. This is for the concave lens. This is for convex lens. This is for concave lens. This formula is very important because one can have also plano-convex lens. Plano-convex means one side is plane, the other side is curved. So in that case, one radius of curvature becomes infinity. So 1 by infinity is 0. So that is possible. So for third case, for plano convex lens, say R1 tends to infinity, then 1 by f becomes n2 by n1 minus 1 into 1 by R2 simply. This is 9. Fourth is for plano concave lens. One side is plane, the other side is concave, plano concave lens. Here also R1 tends to say infinity, then 1 by f is equal to minus n2 by n1 minus 1 into 1 by R2. So, this is equation number 10. So, these are the special cases, and then an interesting effect of this formula is that a lens has a focal length, suppose 10 centimeter in air. Then if that lens will be immersed in water, then the focal length will be more than 10. That has been theoretically established and experimentally verified. So, the focal length of a lens not only depends on the construction, but also on the surrounding medium. So, medium has an effect regarding the focal length. Also, sometimes if the surrounding medium has a refractive index greater than that of glass, so the lens behaves like a divergent lens. So, a convergent lens becomes a divergent lens under specific condition. So, then we come to the optical instruments. So, first is simple microscope. Simple microscope. So, here it is nothing but a lens, convex lens with a holder. Convex lens, optical center is at P and focal length is focus is here. So, if the object say AB is like this, object is at in between focus and optical center, then the ray travels like this, passing through the focus on the other side. Then another is we can pass through the optical center, and by definition of optical center it will go straight. So, if you produce them backwards, then suppose they meet, they appear to meet here, and you will have a virtual magnified image A dash B dash. So, A dash B dash is the virtual magnified image, and you can keep your eye close to the lens. Suppose the eye is not kept very close to the lens like this. Suppose this is the eye and one is has kept like this at a distance say A from the convex lens. Then what will happen? You see object is U, object distance is U, that is here, and image distance is V. Image distance is V. For clear vision, the image should be nearly 25 centimeter from the eye. called least distance of distinct vision. In short, we write like this: LD dV, which is about 25 centimeter for most of the persons. So this one is your, say, suppose D, it is like this. From I it is like this. So what you see from this one? What is V? V will be D minus A. So then length equation is 1 by V minus 1 by U is equal to 1 by F. So here you write 1 by D minus A, and it is measured, ray direction is from left to right, you are measuring from right to left, so you can associate a minus sign. Similarly, U is measured from right to left due to sign convention, so it is also minus U. Then focus is on the right hand side, so it is positive. Then multiplying by D minus A throughout, we have. So you multiply by D minus A, so this will be minus 1, then plus D minus A by minus U is equal to D minus A by F, and this one is your magnification. Why? Because magnification is minus V by U. So it is minus, then V is this one by U. So magnification, which is written as M. So this gives you M is equal to 1 plus D minus A by F. So this is your equation 1. This is for the case when eye of the observer is kept slightly away from the convex lens. But if the eye is very close to the convex lens, if A tends to 0, then M is equal to maximum. M is equal to maximum is equal to 1 plus D by F. That is your equation number 2. So this is possible, and by this detective persons or old people, they have a holder with a lens, and they can read small letters, they can read. So this is about the simple microscope. Then we come to the compound microscope. Compound microscope. So compound microscope is a device by which one can observe very small things with a greater magnification than that of the simple microscope, because simple microscope has some limit because of the formula, as you see from this 1 and 2 formula. So they have a limitation, but for the compound microscope there is arrangement for 2 lenses, 2 convex lenses placed in a tube. First convex lens may be small, no problem, because the object to be viewed is small. So, this is a towards the object. So, it is called objective lens. This is FO, F objective. Then you can have 2FO, also 2FO this side. Why we are writing 2FO and these things? Because as you see that if the object will be between FO and 2FO, object is small, say AB, then it sends rays, one ray through PO, the other goes through, one is through the optical center and the other is passing through the FO. So, this is first ray, this is second ray. So, you have a magnified image, magnified but inverted. So, it is A dash B dash M. Then what to do? The second lens is to be placed. Second lens must be of large aperture to receive the rays. This is a PE. PE means it is called eyepiece. The focus of the eyepiece is FE. FE this side and also FE this side. The first image formed by the objective must lie between the focus and optical center of the eyepiece. Then what happens? To form the image by the eyepiece, you pass again the same procedure. We pass a ray, pass a ray through the optical center, which goes straight, and the ray which is parallel to the principal axis passes through the focus. But as you see, they diverge. So, therefore, you have to extend it backwards to get the virtual magnified image. And this image you can say A double dash, B double dash. And here also a same way you can keep the eye close or away, but for greater magnification the eye should be close to the eyepiece. Eye must be close to that, so that your A, small a of the simple microscope becomes 0. So, here what happens? Here this is your D, least distance of distinct vision, and that is also equal to VE. Let us not write about the sign conventions, it is VE. Similarly, it is also UE. U2 you can write or say UE, better, U eyepiece. And here it is UO. And this is your first image is formed, say VO. And the distance between the objective and the eyepiece is called tube length. Tube length is the distance between objective and eyepiece. And in our diagram, as you see, it is VO plus UE. So, this is the formation of image, and it has been magnified twice by the objective and also the eyepiece. So, what happens? Let us say write the M, that is the magnification. Magnification is equal to size of the final image by size of the object. So, it will be size of the final image is your A double dash B double dash by AB, and this we can write as A double dash B double dash by A dash B dash, then A dash B dash by AB. So, why we have written like this? Because you see A dash B dash by AB is the magnification by the objective, that is MO, and A double dash B double dash by A dash B dash is your ME. So, ME MO is equal to M, that is the product of the magnifications. So, what is ME? ME, as you see, is I is closed, so it is D by FE, and MO is your V by U. So, V by U, that is V is your VO, VO is positive and UO is negative. But if you consider the magnitudes, then they become VO by UO. So, this is the expression for the magnification by the compound microscope, and it is largely used in +3 classes. So, the cross wire to measure the size of the objects and images, cross wires are used. So, in the cross wires are to be placed at the site of the first image, that is A dash B dash. So, cross wire is like this, is placed at A dash B dash to measure the size of the image or object. So, these are necessary for the measurements, and then we come to the telescope. So, telescopes are instruments which can help us to measure and observe objects at a great distance. To observe at a great distance, your telescopes are used. And they are of two types. One is called refracting and the other is called reflecting. So, it is refracting, that means lenses are used, and the other is reflecting, where mirrors are used. And refracting are of three types, that is your astronomical, then one is terrestrial, then the other is Galilean. And reflecting telescopes are of two types. One is called Newtonian, the other is called Cassegrainian. In the NCERT book, they have only explained a little about the Cassegrainian type, but Newtonian they have not explained. And usually we use these astronomical telescopes, but the one drawback is that they produce inverted images. To make them erect, terrestrial is used. And Galilean telescope has a concave lens as well as a convex lens. So, they make erect images, and Newtonian uses a large concave mirror with a hole, and the Cassegrainian is also like that. We will go to that if time permits. Then let us come to the astronomical type of telescope. Astronomical. Telescope. So, it is similar to compound microscope, as it has two convex lenses. Two convex lenses inside a metallic tube. Inside a metallic tube, and there is arrangement to change the positions with the help of a screw, and it is used in two ways. Number one is when focused to infinity, and number two is focus to LDDV. So, focus to infinity, let us discuss. The objective of the lens must be large, so that it can receive more rays. So, it is objective. This is a PO. Rays are usually inclined coming from long distance. Suppose this angle is alpha, and they form the image, say AB, on the focus FO. On the focus, a real but diminished image AB is formed, and if you adjust the eyepiece in such a way that the eyepiece, if you adjust the eyepiece in such a way that the two foci FO and FE coincide. This is your FE, this is principal axis. Then what happens? This is the focal length for the objective, and this is the focal length for the eyepiece, and these two coincide, and this you know the tube length. Tube length is your FO plus FE. In this case, tube length is from objective to eyepiece, and this angle made by this one is a beta. Here this M is called the angular magnification. Angular magnification. The point is, why we are not saying it as magnification only? Because you see, object is at infinity, so object distance is infinity, and image is also formed at infinity, because you see from this diagram that they go parallel to each other, so they will meet at infinity. So therefore, magnification usually is V by U with a minus sign like that. So, it becomes infinity by infinity, which is meaningless. So, that is why we define angular magnification is equal to angle subtended by the image at the eye divided by angle subtended by the object at the eye. You see from the diagram that it is nearly equal to beta by alpha, because you see that the image final image is at infinity, very large, but it makes an angle beta with the eyepiece, and eye is close to that eyepiece, eye of the observer. So, it is beta. Then for alpha, it is not actually angle made by the object is infinity. It makes an angle alpha with the objective, but compared to this object distance, the tube length is small. So, therefore, we can take that the object also makes an angle alpha with the eyepiece or the eye. So, and this is these things are at a great distance. So, angles are small, alpha and beta are both small. So, you can approximate as tan beta by tan alpha. And from the diagram, you see that tan beta is your AB by FE divided by, for tan alpha also you find AB by FO. So, it is FO by FE, and this expression suggests that the focal length of the objective should be much greater than the focal length of the eyepiece. In order that you will have a greater magnification. So, that is for the, and the crosswire, as you know, it can be placed at AB, first image, that is AB. So, crosswire can be fitted with this one. Then second one is called focus to LDDV. The same astronomical telescope can be adjusted so that it would be focused to LDDV. And here, what is the change in the diagram? Here the change in the diagram will be, first part is as before, then the second part, for the second part, this first image has to be formed in between the focus and the eyepiece, optical center of the eyepiece. So, FE will be here. If FE will be here, then this ray goes straight, no problem, but this one will go like this. This is your FE. So, when they are produced backward, they will produce a virtual image, virtual magnified image, of course. So, virtual magnified image, say A dash, B dash. So, here the tube length will be FO, this is FO, and this is not FE. This we wrote as FE, but it is now UE. This is your UE. So, your tube length is now FO plus UE. And magnifying, angular magnification is as before, beta by alpha, tan beta by tan alpha. So, it is tan beta is nothing but AB by UE. You see it is by UE, and this one is AB by FO as before. So, it is ultimately what you find, it becomes FO by UE. But the problem is how to know UE, because you see inside the tube, metallic tube, the two lenses are there, and you are finding the final image, you are seeing the final image. So, therefore, this UE has to be avoided. To avoid this UE, what we do is we will write say lens equation. So, lens equation for the eyepiece. The eyepiece is 1 by VE minus 1 by UE is equal to 1 by FE. And here your VE is nothing but capital D, that is your least distance of distinct vision. So, it is 1 by D minus 1 by UE is your 1 by FE. But here you have to be careful, because the D is measured from the PE, that is your optical center of the eyepiece. So, we have to put a negative sign due to sign convention. So, that gives you 1 by UE. 1 by UE is your 1 by FE plus 1 by D. That is your FE D, then D plus FE. There is a minus sign. So, for UE also that you have to have a minus sign, because you are measuring object distance from PE to this, which is left, right to left. So, it is a minus sign, so it becomes plus. Then using equation 2 in equation 1, what you find? You find M. So, M will be FO into D plus FE by FED, and it is FO by FE, then you divide by D. So, it becomes FE by D. So, it is third equation. So, this is the final expression for this case, and the terrestrial telescope will go very briefly. Terrestrial telescope is an astronomical telescope where provision is made to make the final image erect. You see from this diagram that the final image is not erect. So, that is why we use another convex lens of suitable focal length to make the image erect. So, how to do that? There is another convex lens. This is for the terrestrial telescope. Another convex lens placed here at the 2F position. So, this is your object at 2f. So, image will be at 2f. And what is the advantage? Here the image is now erect. Then what you do, as usual, you have the eyepiece. Eyepiece is there. And the focus has to be this A dash B dash must be in between the focus and the optical center. So, second one goes like this, and the first one will be like this, and they are to be produced backwards. To get the final virtual image A and double dash, then B double dash, and this is at a distance capital D from the eye of the observer. So, what happens to the tube length? So, tube length is now, this is UE, tube length is now FO plus 4F. FO plus 4F, that is for this middle convex lens. plus UE. So, here the advantage is that final image is erect, no problem, but the tube length has increased, maybe to some inconvenient length, so that one faces difficulty in adjusting the lenses. That is FO plus 4F is introduced. Suppose focal length is 10 centimeter. For the convex lens, it will be 40. So, 40 plus FO is something, then UE, so it becomes very large. And the other disadvantage is that the three lenses are there, so they absorb light to greater extent. So, the final image is little blurred. Blurred means this is not very clear. It will be observed, but it will be not very sharp. So, that is one disadvantage, but the advantage is that you have the final image erect. So, this is what the terrestrial telescope. Then Galilean is there, the concave lens and convex lens. Then these two things, they have the concave mirrors to have the image. And the NCERT book also has no formula for the magnifications for the reflecting telescopes. So, therefore, they are just used to observe the things. So, that is all. Today